2.8, combining functions. Two functions can be combined to form new functions such as f plus g, f minus g, f times g, or f divided by g, and vice versa. So let's let f and g be functions with domain A and B respectively. So if we add f and g of x, that is the same as f of x plus g of x. Our domain is A intersect B. F minus g of x is the same as f of x minus g of x, and our domain is A intersect B. F times fg of x is the same as f of x times g of x. Our domain is A intersect B. And f over g of x is the same as f of x divided by g of x. And our domain is x, where x is in A intersect B, and g of x does not equal 0 because we can't divide by 0. So we're going to let f of x equals x cubed and g of x equal root x. We're going to find the following and state their domains. Okay, so we have f plus g of x, same as taking f of x, which is x cubed plus root x. And we actually cannot combine these any further. Our domain is x, where x is greater than or equal to 0, because we cannot take square roots of a negative number. F minus g of x goes to x cubed minus root x. We can't make this out any further. Same domain as before. F times fg of x means we take x cubed times x root x. Let's rewrite root x as 1/2. And when same bases are multiplying, we add the exponents. So it goes to 7 halves, x to the 7 halves. Same domain as before. F over g of x, or taking x cubed over root x, goes x cubed over x to the 1/2. Subtract the exponents at x to the 5 halves. Same domain. F plus g of 4. So now we actually have a number. Before, we just had x. So now we need f of 4 plus g of 4. So we take 4 cubed plus root 4 goes to 64 plus 2, so we get 66. 66 is your domain, so we don't need to state it explicitly. F minus g of 4, so we're taking f of 4 minus g of 4. We actually just worked those out, so that goes to 64 minus 2, and we get 62. Don't need to state the domain. F of g of 4, that means to take f of 4 times g of 4. Alright, so that goes to 64 times 2. Gives us 128. And lastly, f over g of 4, that means f of 4 over g of 4. 64 divided by 2, 32. The graph of the function f plus g can be obtained from the graphs of f and g by graphical addition. This means we add the corresponding y values. So if we have g of x as this linear equation, we have f of x as such, we would just transpose the purple on top of the green. And so the purple is f of x, and the red is now f plus g of x. Now we're going to talk about composites of functions. Given two functions, f and g, the composite function f of g is defined by the following. F of g of x. The domain of f of g is the set of all x in the domain of g, such that g of x is in the domain of x. It's defined when both g of x and f of x are defined. So this will make more sense with the following example. We have f of x equals x squared minus 3, and g of x equals x plus 5. So we're going to find f of g of x and g of f of x first. So for f of g of x, that really means to take f of g of x. So wherever we see an x in the outer one, such as x squared minus 3. So this is the outer, and g of x is inside. So g of x is going in for x. So instead of x squared minus 3, we're having x plus 5 squared minus 3. So we would FOIL this, x squared plus 10x plus 25 minus 3. So f of g of x is x squared plus 10x plus 22. G of f of x is g of f of x. So we're taking f of x and plugging it into g. So instead of x plus 5, we're plugging in x squared minus 3 plus 5. So g of f of x is equal to x squared plus 2. We are now being told to find f of g of 5. And we already found f of g of x. So wherever we see an x, we're now plugging in a 5. 5 squared plus 10 times 5 plus 22. This goes to 25 plus 50, that's 75 plus 22 gives us 97. For g of f of 16, we're going to use that g of f of x, what's x squared plus 2. So it becomes 16 squared plus 2. Oops, I'm sorry, it should be just 6. Six squared is 36 plus 2 is 38. Finding the composites of functions, we're given that f of x equals root x and g of x equals root 2 minus x. We're going to find f of g, g of f of f, and g of g. So to start, we have f of g. We're going to take f of x, which equals root x, and g of x, which equals root 2 minus x. Okay, so for f of g of x, g is inside, so we're taking this, plugging it in for x equals root from the original and root 2 minus x. Now we're taking square roots, and 2 squares go to fourth root. So it becomes the fourth root of 2 minus x. Our domain is where this exists, so that means our domain exists where 2 minus x is greater than or equal to 0, so x is greater than or equal to negative 2. So we would write domain exists where x is greater than or equal to negative 2. Nope, it should be less than. For g of f of x, we're taking f and plugging it in for x in the g. So this becomes root 2 minus root x. And there's no need to simplify this. This is fine. So this occurs where root x is greater than or equal to 0. So then x has to be greater than or equal to 0. It also occurs when 2 minus root x is greater than or equal to 0, which if we solve that out for x, x is greater than or equal to 4. Less than. I keep forgetting to flip my arrow. So we are limited on both sides. Our domain occurs where x is greater than 0 and less than 4. You could also use interval notation from 0 to 4. Up next, we have f of x. So we're going to be using f twice. So we're plugging in root x into itself. So we get root of x, which becomes 4th root of x. And our domain, x has to be greater than or equal to 0. Or you could use interval notation from 0 to infinity. Finally, we come to g of x. We plug in g to itself, so we have 2g of x's. Plugs into itself, so g of g is the same as root 2 minus root 2 minus x. For your domain, you have to do 2 separate parts. 2 minus x is greater than or equal to 0, so x is less than or equal to 2. Also, 2 minus root 2 minus x has to be greater than or equal to 0. So 2 is greater than or equal to root 2 minus x. Square both sides. 4 is less than or equal to 2 minus x. And it works out to be that x is greater than or equal to negative 2. So we're limited that it has to be less than or equal to 2, greater than or equal to negative 2. So interval notation would give us negative 2, 2.